everyone, and thank you for the introduction, and thanks to the organizers for inviting me. I'm really sorry I cannot be there with you. I was supposed to come, but had to cancel last minute because both my wife and my kids tested positive for COVID, so it didn't seem safe to travel, even though it looks like I evaded COVID in the end. But anyway, so thank you for having me remotely. I will talk about spatial search. So this is kind of the same topic as what Tom introduced, but of course, a different perspective. This is a joint work with Simon Appers, Shantanav Chakraborty, and Leonardo Novo. The paper is on the archive. We put it in December last year, and it's currently submitted. So we're waiting for reviews. Here's the structure of the talk. First, I will remind you about the problem of spatial search, and in particular, spatial search via continuous time quantum walk. So this is an important difference with Tom's talk. This is continuous time quantum walks. I will explain the Childs and Goldstone approach. I will then introduce some more recent tools, like the quantization of Markov chains. This is not so recent, but more recent tools like quantum fast forwarding of random walks, which we will use to go beyond the Childs and Goldstone approach. And finally, I will get to our work, general quadratic speedup for search by continuous time quantum walk. Okay, so here we talk about continuous time quantum walk. So as you probably know, there are different models of quantum computation. Probably the most common ones are digital. So time is discrete, and your qubits will evolve under the action of unitary gates that are applied one after the other. Of course, this is more related to what we do in computer science for classical computation. But of course, as physicists, we prefer analog models of quantum computation because, of course, in most models of physics, time is continuous. And in that case, we have particles like spins that could encode those qubits that will evolve continuously in time under the action of some Hamiltonian according to the Schrödinger equation. So, of course, you all know this. And in these analog models of quantum computation, continuous time quantum walks is just one such model where you have this unitary, this Hamiltonian evolution. Here we will use continuous time quantum walks to solve algorithmic problems, and sometimes computer scientists don't know exactly how to understand this because they are more used to the digital models, and they wonder what is the motivation to look at these analog models. So one motivation coming from physics is that you can study the computational model of computational power of these models by finding inspiration in the dynamics of physical system. And also you can use this intuition about physical system to come up with new quantum algorithms. And the thing is, even if in the end you want to implement your quantum algorithms on a more standard quantum computer, like a discrete gate-based quantum computer, typically you can translate those analog quantum algorithms into the circuit model by using Hamiltonian simulation techniques. So even if you prefer more standard digital models, still starting from analog models can be useful because sometimes it provides a different intuition. So this is kind of the motivation. And here in this talk, we will focus on one particular analog model of quantum computation, which is a continuous time quantum walk. So we will use this continuous time quantum walk to solve algorithmic problems. And actually, the problem we look at in this talk is the same as in the previous talk. It's a search problem. Typically, you have a graph. You can walk on this graph, and one or several of vertices of the graph is marked, and you're looking for a marked vertex. But actually, it's not. Continuous time quantum walks can be used to solve other algorithmic problems. For example, they've been used to solve Boolean formulas, first these so-called NAND trees, and actually first these NAND trees were solved optimally using a continuous time quantum walks, and later it was generalized to arbitrary Boolean functions, and actually it could be proved, we could build optimal quantum algorithm to evaluate some Boolean functions based on this intuition that came up from this quantum walk on the NAND tree. Another interesting contribution is here it's a very contrived problem. Maybe you have some kind of maze where you have an entrance and an exit, and you're looking for you're given the entrance, you're looking for the exit, and it can be shown for some graphs, for example, the graph that looks like this, you can actually get an exponential speedup. So typically for these problems here, you only get polynomial speedups, but actually there are some problems. You can set up problems where quantum walks can provide an exponential speedup over classical algorithms. It's been shown that any algorithms that can be implemented on a circuit-based quantum computer can also be implemented as a continuous time quantum walk. So this model is actually universal for quantum computation. So this is just to have a broad picture of what we can do with continuous time quantum walks, but in this talk we will focus on this search problem again. So in order to fix notations, you probably all know that, but let me just remind you basic notations. So we have a graph. The graph can be described by its adjacency matrix A, which is a Boolean matrix, with a 1 whenever I and j correspond to an edge of the graph. You can also look at the degree of each vertex and form a diagonal matrix with those degrees, and then you can define the graph Laplacian which would be this diagonal matrix D minus the adjacency matrix. And this matrix somehow encodes the connectivity of the graph. And if you look at continuous time classical random walks, then you can if Pj of t describe the probability of a particle lying in vertex j at times t, then if you have some hopping rate by unit of time, you have a probability gamma of jumping from one vertex to one neighbor, then you can show that the differential equation that describes the dynamics of the walk is given by this expression here. So this is for continuous for classical random walks, and for continuous time quantum walks, the most studied model is as follows. We use again this Laplacian, but instead of using this Laplacian in this stochastic equation, we use it in Schrödinger's equation using as Hamiltonian again this Laplacian. Again, you can put some parameter gamma which encodes some rate, some interaction rate. And then the dynamics will be described by this differential equation. And of course, as you all know, Schrödinger equation causes a unitary evolution. So you can, the quantum state at time t is given by this expression if psi of 0 is a state at time 0. What is maybe interesting is to compare with what we had for classical random walks. The differential equation was this one. So you see it's essentially the same, except that you have an I here. And you can also find the solution for the classical. You can also express it at some exponential, but again, here it's a real exponential, and here it's a complex exponential. And as you all know, even though these two evolutions look mathematically, if you look at the equation, they look very similar, you know that the dynamics will be very different. Here you have a random stochastic dynamics, and here you have a unitary evolution. And in particular, if you, for example, you look at a very simple graph, just a line, and you start from some given vertex, and you first evolve classically. Over time, the distribution, which was just a peak in one position, would just look like a Gaussian. And for the classical walk, the standard deviation of this distribution will scale as the square root of the time. So actually, the variance will be linear in the time. Whereas if you set up the quantum walk now, and you start also from a given vertex, the dynamics will be completely different. Actually, you will have two waves, one wave going ballistically to the right, another wave going ballistically to the left, which means that actually now the standard deviation will be linear in t. So in a sense, we already see here that quantum walks spread quadratically faster. And the idea of using quantum walks to solve algorithmic problems is that hopefully we can exploit the fact that they spread quadratically faster to solve some problems faster. In particular, we hope that for spatial search problem, maybe we can also get some kind of quadratic speedup using quantum walk instead of classical random walks. Okay. So let me now explain the most basic continuous time quantum walk algorithm, which was introduced by Childs and Goldstone already in 2004. So it was quite a while ago. In that case, again, you use as Hamiltonian the Laplacian with some interaction gamma. And since you want to encode the search problem, you need to encode somehow which states are marked. And here the idea is that you will just give an energy penalty to the vertices that are marked. So you just add some diagonal term here to your matrix, to your Hamiltonian for the marked vertices. Here there's only one marked vertex for Childs and Goldstone. Later we will also consider the case of multiple marked vertices. When so we could replace L by the adjacency matrix, we would get similar results. So what did Childs and Goldstone observe when we look at the dynamics of these quantum walks? Well, they looked at different graphs, like these typical graphs, the complete graph, hypercube, and lattices. And what they see is that often they get these quadratic speedups. So the classical random walk would take time of order n to find the red vertex here, whereas by using a quantum walk for the complete graph or the hypercube, it will only take a time square root of n. And we can also show that square root of n is optimal because actually the complete graph corresponds more or less to the Grover problem. And we know that for the Grover problem, we cannot find a marked vertex, a marked element in less than square root of n steps. So we know that this is optimal for the complete graph. And for other graphs, when you remove edges, you can only make your problem harder. So you can show by reduction that this is also optimal. For lattices, the situation is not so simple. For dimensions strictly larger than 4, it's still optimal, but actually for dimension 2, 3, or 4, you do not get a full quadratic speedup. And we will mention this also later. Okay, so from this basic, sorry, a question? Okay, so I thought I heard something. Okay, so if you have questions, do not hesitate to just stop me at some point. So after this first paper, caused a long line of research. People were looking at other graphs, how to get optimal speedups on those graphs, how to fix the problem for lattices of lower dimensions, and so on. And people tried to understand in which cases we could get a good speedup. And I would just mention a few papers. The first two actually are co-authors by Tom. And he with his co-authors, they show, for example, it looks like the connectivity helps for getting an optimal speedup. It's not always the case. So they could provide a counterexample where it shows that the connectivity does not necessarily help to find the right vertices. Also, the symmetry does not necessarily help. So the question, how can we solve the problem? For example, for lattices, as I've written here, for dimension 4 or less, we did not have a full speedup. Well, Childs and Gay showed that by introducing some internal degrees of freedom on the particles moving on the graph, you could actually improve the behavior for lower dimensions. Also, for example, a more recent work by my co-authors showed that if you take a random graph, actually with high probability, with probability going to 1 as the size of the graph increases, you get an optimal speedup. So actually the cases where you don't get an optimal speedup are kind of accidents, but that doesn't really help because sometimes these are the graphs we need. So for example, lattices are very common graphs, but they happen with probability 0 if you take a random graph. So, but anyway, it looks like having an optimal speedup is actually quite generic if you just take a random graph. Okay. Also, one thing we can show is that a large spectral gap. So if you look at the gap of the Laplacian, for example, a large spectral gap is sufficient for optimal quantum search. But it's sufficient, but is it necessary? And in more general, can we get a more general sufficient condition for optimal quantum search? And this is something we tried to do in a previous paper with my co-authors from a couple of years ago. And what we could show, I will not go into the details, but if we take just the usual Childs and Goldstone Hamiltonians, or just the Laplacian plus an energy penalty for one marked vertex, this only works for one marked vertex, we could show first what is the optimal interaction rate gamma, and then with this optimal interaction rate gamma, what is the optimal time at which we should stop, and what is the best success probability? And doing so, for example, if you look at this expression, you see that if S1 squared over S2 is a constant, then actually you get, this will be a constant too, and then you get a square root of n time, which is optimal. So actually we get this very general sufficient condition for the optimality of the Childs and Goldstone algorithm. So for any graph where this, so S1 and S2 are given by these elements that you can compute from the eigenvalues and eigenvectors of the Laplacian. And this gives a very sufficient condition, and it's quite general. Actually, it reproduces, as far as I know, essentially all previous examples of optimality that you can find in the literature. Nevertheless, what we could also show in this paper is that this sufficient condition, sometimes it's not satisfied, and for some graphs, you cannot get an optimal speedup. And here is an example. For example, we called it a roue graph because if you look at a chessboard and you consider that each position on the chessboard is one vertex, and you draw an edge between two positions, if you can go from one position to the other using a move of a rook, then for some rectangular chessboards, for some values of n1 and n2, you can show that it's impossible to get a square root of n speedup, so quadratic speedup. So there are some cases where indeed you cannot get quadratic speedup. This was the situation a couple of years ago, and the question is, how can we go further? How can we maybe modify the quantum walk to get an optimal speedup for all possible graphs? Before I explain this, I will again come back to the classical problem and explain the classical problem that we would like to speed up. So when I say we would like to get an optimal speedup, I need to say an optimal speedup with respect to what? So in general, if your classical walk can find your marked vertex in time proportional to n, then you would like something like square root of n. But sometimes the classical walk does not find the marked vertex in time n. So in that case, how do you quantify the speedup? So in general, if you take a general graph, you have a set of vertices, and some of them are marked, they are in red, and some of them are not marked, they are in gray here. If you set up a Markov chain on this graph, then this Markov chain is described by a stochastic matrix P, and then you know, as long as P satisfies some regularity condition, if it's ergodic and reversible, then P has the unique stationary state. Actually, if P is symmetric, this stationary state is even the uniform superposition over all vertices. Okay, so if we have this random walk over this graph, the question is, what is the algorithm that we would like to compare our quantum walk with? And here is the algorithm. The algorithm is very simple. You start by picking just a random vertex according to this distribution, and then you start walking on the graph. And each time you reach a new vertex, you check if it's marked or not. If it's marked, you're done. You just output this vertex. If it's not marked, you just move to the other one. You check again if it's marked or not, and you continue like this. Okay, and classically, the expected number of steps that you will require until you hit one of those marked vertices will be given by the quantity being called the hitting time. So the hitting time depends, of course, on the Markov chain P and on the set of marked vertices M. In particular, just to give you an example, if this was a complete graph and there was a single marked vertex, then the hitting time would just be n. Okay, proportional to n at least. Okay, so that's the problem we would like to speed up. Now we would like to set up a quantum walk that solves the same problem, that finds one of these red vertices in a time, hopefully, square root of this hitting. Can we do this for any graph, for any Markov chain P? That's the question we would like to answer. Okay, so of course, we could try to do this using the Childs and Goldstone approach, like the one that I've talked about earlier, but there are problems. For some graphs, it doesn't work. In particular, also, it doesn't work for multiple mark nodes. Actually, we don't have general results for the performance of the Childs and Goldstone algorithm for multiple mark nodes. What we did in this previous paper here, it was only for a single mark node. Okay, so we don't have any analog for multiple mark nodes. And we also know that for some graphs, this does not provide a quadratic speedup with respect to classical hitting time. It's the case, for example, for this rook graph. Also, how can we define a continuous time quantum walk for any Markov chain P? you could do it, but it's not always clear that there's a connection between the spectral properties of P and the spectral properties of your quantum walk. And because of this, it's not clear you can make a connection between the performance of the quantum walk and the performance of the classical walk. So we need to solve those problems. And essentially what the properties we would like are as follows. We would like to be able to define our algorithm for any ergodic reversible Markov chain. We would like to be able to provide a quadratic speedup for a single Mark node. So that's the first step. And then we would also like to be able to deal with multiple Mark nodes. So we'd like to at least to give some performance guarantee for multiple Mark nodes, and hopefully show that this performance guarantee is that we get a full quadratic speedup for multiple graph nodes. And let's look at some papers. Let's look essentially at the state of the art a couple of years back, a few years back, say. So as I've said, for the Childs and so for continuous time quantum walks, for the Childs and Goldstone approach, we can. It's not clear we can define it for any ergodic reversible Markov chain. It does not provide a quadratic speedup for all graphs, and we don't know what happens for multiple Mark nodes. Now, if we look at other models of computation, for example, this adiabatic model, which inspired a discrete time quantum walk, which is just a discrete time quantum walk, so a secret-based algorithm, if you want. In that case, we could at least solve the first three problems. So define a walk for any ergodic reversible Markov chain, provide a quadratic speedup for a single Mark node, and give a performance guarantee for multiple Mark nodes. But unfortunately, this performance guarantee was not a full quadratic speedup. Actually, it was a quadratic speedup related to another quantity called the extended hitting time. And this extended hitting time is the same as the hitting time for a single Mark vertex, but not for multiple Mark vertices. So that was the situation a few years ago. Now, a couple of years ago, there were two results. First, in the context of continuous time quantum walks, we could show with my co-authors, we could actually get something equivalent to what we have with discrete time quantum walks by modifying the quantum walk. So we do not use the Childs and Goldstone continuous time quantum walk. We use another one, and we could solve at least the first three problems, but we do not have a full quadratic speedup for multiple Mark elements. Now, for discrete time quantum walks, again, a couple of years ago, Ambainis et al. Could solve the last problem, providing a full quadratic speedup even for multiple Mark nodes. And inspired by this result, by using some variation, it's not immediate how to go from here to here. What we could show, and this is what I'm presenting today, we could show that with the continuous time quantum walk, we can also tick all four boxes here. So essentially get a full quadratic speedup with respect to continuous classical random walks for any ergodic reversible Markov chain. Okay, so how do we do that? We need several tools. The first tool is already old. It's a tool introduced by Szegedy in 2004 that allows from any ergodic reversible Markov chain to define some discrete time quantum walk. So a unitary operator W of P. And this could solve, it could show that we could get a quadratic speedup for the detection problem. So what is the detection problem? Remember, the problem we really want to solve is we have a graph, there are some Mark vertices, and we would like to find them. So using this technique, what Szegedy could show is that he could not necessarily, for some graphs, he could not find the marked elements, but he could at least detect their presence. So he could discriminate between a graph with no marked vertices and a graph with marked vertices. So later, using a technique called interpolated Markov chains, with some co-authors of mine, we could show that we could get a full quadratic speedup, at least for a single marked element. So essentially, we use also this technique of Szegedy, combined with interpolated Markov chain to get the full quadratic speedup to find the marked vertices, not only detecting them, but it only worked for a single Mark vertex. Then finally, a couple of years ago, combining these techniques with a other technique called quantum fast forwarding, Ambainis et al. Could solve the general problem using a discrete time quantum walk. They could get a full quadratic speedup even for multiple Mark vertices. So this is the situation before the work I'm presenting today, and this uses discrete time quantum walk. And what we would like to do is to get the same thing for continuous time quantum walk. Okay, but let's first, since we will need these three techniques, let's go over these three techniques one by one. I will go a little bit quickly because I don't have time to explain all the technical details, but I will try at least to give you a flavor of the idea. So this technique by Szegedy start with the stochastic matrix encoding some random walk, some classical random walk, and it sets up a unitary operation that encodes that allows you to do some discrete time quantum walk on the graph. Actually, one difference is that we will not walk on the vertices of the graph, but on the edges of the graph. Okay, so this is why actually we have a Hilbert space which spans essentially by the vertices of the graph, but it's double. We have twice this Hilbert space. Okay, and then we can set up states psi x, which are essentially superposition over all the edges that touch some vertex x. And then we can set up these operators here. We'll not go into the details. We also have this swap operator that Tom used in his talk that just swaps the vertices. Actually, at least it's equivalent to what Tom did in his talk. So this is actually the walk that really performs the one step of the walk. Okay, and then if you want, this operation is somehow the coin operation, and this operation is somehow the walk operation. So Szegedy, using this construction, he described, he built a unitary matrix that encodes some quantum walk on the edges of the graph, and what is interesting is that there is a close connection between the spectral properties of W and the spectral properties of the stochastic matrix P that we started with. And that's how you can get these quadratic speedups, because really the complexity of the classical walk relates to the spectral properties of P, and the complexity of the quantum walk relates to the spectral properties of W. And since these are both related, we can get the connection between them. Okay, note that, as I said, this is a walk on the edges of the graph. So for example, if in your graph you have three vertices A, B, and C, then this unitary operator W will couple the edges A, B, and BC, for example. And we will do something similar for all continuous time quantum walks. So this is something which is different to more like the Childs and Goldstone approach, where really the Hilbert space is just a position. So you just walk really on the vertices and not on the edges. He also, for example, I said that there's a close spectral connection between W and P. And for example, W has an eigenstate with eigenvalue 1, which is just like a quantum encoding of the stationary distribution pi. Okay, so this is for Szegedy quantum walks. Very quick introduction. Now, interpolated Markov chains, intuitively, it's quite simple. So suppose you have a Markov chain. And in this Markov chain, you have some vertices which are marked and some vertices which are not. Okay, so for example, here the red vertex is marked and the blue vertex is not marked. If you look at our classical random walk search algorithm, what we do, we walk on the graph until we hit a marked vertex. So essentially, you can interpret this algorithm as saying that the marked vertex is absorbing. When you hit the marked vertex, you stay there, you stop your algorithm, or you just stay there, you don't move anymore. So this means that actually the actual stochastic evolution is not really this Markov chain, but actually this absorbing Markov chain, where the transitions from the marked vertices are just replaced by the identity, by self-loop, if you want. Okay, so you replace any outgoing edge from marked vertices by self-loops. And this is really what this random walk search algorithm does. Something that you can do, and that might seem useless, but that is actually very useful, is to interpolate between these two. So now you can replace the outgoing edges only with some probability S by a self-loop. So now when you hit a marked vertex, with probability S, you stay there, and with probability 1 minus S, you leave it. And actually, what is interesting, so this describes another stochastic matrix P of S. And what is interesting is that, for example, the stationary distribution of P of S, well, S equals 0 is just the stationary distribution of P. And when S goes to 1, it will be the stationary distribution of P prime. But what is the stationary distribution of P prime? Since P prime is absorbing, well, at some point you will hit a marked vertex and you will be absorbed. So the stationary distribution only has weight on the marked vertices. So if you get to the stationary distribution of P prime, you're done because all your weight are on the absorbing vertices. And the nice thing about this interpolated Markov chain is that it allows to interpolate the stationary distribution between one and the other. And the thing is, now you can take the Szegedy equivalent of this interpolated Markov chain, and in that case, the eigenstate with eigenvalue 1 of W of S, so the quantum walk corresponding to P of S, will also interpolate with between uniform superposition over all vertices and all the weight on the marked vertices. So if you can interpolate between these two eigenstates, essentially you solve a problem. You start from a uniform superposition over everything, and then at the end you only have everything on your marked vertex. And this is essentially, without giving any details, the intuition behind this first algorithm that could show a quadratic speedup for all Markov chains with a single marked vertex. But unfortunately, it didn't work for multiple marked vertices. But then a couple of years ago, Hamiltonians et al. Used another technique called quantum fast forwarding to solve the problem for multiple marked vertices. The idea of quantum fast forwarding, I give you the main equations here, but again, I don't really have time to go into the details. But the idea is that when you study a stochastic matrix P, it's always interesting to look at the discriminant matrix D, which is somehow a symmetric version of P, a symmetrized version of P. And you can show that D and P have the same eigenvalues, they are similar, so they have the same spectral properties. And the idea now we will work with D instead of P. And what we will look at is the tth power of D. And you can interpret this as being what happens when you apply T times the classical random walk P. And what we can show is that D to the T can be written as a linear combination of W to the J, where W is the Szegedy walk, so the quantum walk. So you can, in a sense, approximate T steps of the classical walk using a linear combination of J steps of the random walk. And the nice thing is that you can even truncate this sum here for T primes over the square root of T. So it looks somehow that using square root of T steps of the quantum walk, you can simulate T steps of the classical walk. So I'm putting a lot of details under the rug here, but this is essentially the main idea. And the nice thing is that it works. The problem, of course, that this is not a unitary evolution because it's a linear combination of it's a convex combination of unitaries. A convex combination of unitaries doesn't have to be unitary, which means actually when you simulate this, you get another state on top of the state that you would really like, that allows you to fix the unitarity of your evolution. So that's why it's not completely trivial, but I cannot go in more details. But what you should remember, in a sense, is that using square root of T steps of the discrete type quantum walk, you can simulate T steps of the discrete time classical walk. And using this idea, what Hamiltonians et al. Could show is that they could simulate HT steps of the classical walk, which would find the marked vertex, using square root of HT steps of the quantum walk. Actually, you do not get full success probability. That's why it's not completely true. It's actually quite hard to compute the success probability, but the success probability is not so low. It's 1 over log of HT. So just by repeating log of HT times, you get success probability close to 1. So you get some extra log factor, but it's negligible. So the leading behavior is still this square root of HT. Okay, so as I said, there are many difficult technical steps, and I cannot go into details because I only have just a few minutes now to talk about what we did. What we did is what we would like to do the same thing using a continuous time quantum walk. So essentially, some Hamiltonian evolution under some time-independent Hamiltonian that encodes some connectivity of the graph. And what we will do again, the idea is that we will use, so we will try to follow the same idea as Hamiltonians et al. So they use the Szegedy analog of the classical random walk. They use interpolation of Markov chain, and they use quantum fast forwarding. So here, what we want to do I think I will. So what we want to do is to use a Hamiltonian analog of the Szegedi walk operator. So here the Szegedi walk operator is just a unitary. So it's a discrete time quantum walk. But there's actually a Hamiltonian that has the same spectral properties of this unitary operator W. It was introduced by Soma and Ortiz in 2010. And they show that you have the same spectral connection. And in a sense, it's very tempting to use this Hamiltonian as a search operator for quantum walk, for the continuous time quantum walk. And by the way, as I said before, this defines a discrete time quantum walk on the edges of the Markov chain. And so by analogy, this will also define a continuous time quantum walk on the edges of the Markov chain, so on the edge of the graphs. So it's not the same thing as the Childs and Goldstone algorithm that implements a quantum walk on the vertices of the graph. Nevertheless, this Soma-Ortiz Hamiltonian has a nice connection. If you know has a nice spectral connection with the eigenvalues of P, and in particular, if you know the eigenvalues and the eigenvectors of the discriminant matrix D of P, you can get immediately the eigenvectors and eigenvalues of this Hamiltonian. And in particular, often the spectral gap is something which is very important. We can show that if the spectral gap for the random walk was delta, the spectral gap for the quantum walk will be square root of delta. So we get already some quadratic improvement. So hopefully we can turn this quadratic improvement into a quadratic speedup for the algorithm. Okay, so now we have essentially all the necessary elements. We have the Soma-Ortiz Hamiltonian, and we would like to use a continuous time version of quantum fast forwarding. This is the missing element. Actually, we can do this using the following idea. So if we look not at H, but at H square, H square is actually, we can show that it's the matrix encoding H square is the same as identity minus the discriminant squared. So already we see why there's a connection between the eigenstate and eigenvalues of these two. But now if we take the exponential of this, this is essentially the continuous time random walk associated to P squared. So essentially 2 steps of P, if you want. So it has the same dynamics overall, maybe up to a factor of 2. This would be the effect of running the continuous time random walk on our graph. And it's equivalent to applying this operator on side. The problem, of course, is that this operator is not a unitary operator. But we can show actually that this operator can be implemented as some kind of linear combination of unitary operators again. And this is called the Hubbard-Stratanovich transformation. Now the idea is that we would like to apply this on our quantum state, and instead we will apply some linear combination of unitaries. Of course, we can apply one term of this. This is just running Hamiltonian H, applying Hamiltonian H for time tau j. But how do we do this? So here is just a discretized version in case you don't like discontinuous variables, but it works for both actually. So this is a discretized version of this integral. And we would like to simulate this convex combination, if you want, of unitaries. And what we can show, I see that I only have a few minutes left, so I will go over the math very quickly. We can show actually that we can simulate this by running the Hamiltonian H for time tau j, with j picked at random from some distribution, just a renormalized version of the CJs of the coefficients in the combination in the linear combination here. So it's actually the algorithm overall is very simple. Once you can apply H, you just pick a random time J according essentially to this Gaussian distribution. You apply it on your initial quantum state, or your uniform superposition over all the vertices. And what you can show is that the probability that you hit a marked vertex, if you measure after doing this, is as good as the probability to do it with the classical random walk, if you want. Okay, so I pushed a lot of details under the rug. I'm sorry about this, but the final Hamiltonian is very simple. So this is how to do this fast forwarding. Now there's one last element that I did not mention. The fast forwarding, we need to do it on the interpolated Markov chain. And if we do that, then for the right parameter S, then we can show that we get the same success probability as in the discrete time quantum walk. and then we can solve the problem that we wanted. Okay, so I'm already a little bit over time, so we just mentioned that this technique can be used to solve the search problem on a graph, but it can also be used to do ground state preparation. So many quantum algorithms rely on ground state preparation of some Hamiltonian as a subroutine, and actually we can use the same trick, this Herbert-Swiatanowicz transform, to prepare the ground state of some systems, and we expect that this can lead to improvement for some other algorithms besides spatial search. Okay, so I will stop here. So in summary, quantum walks are natural ways to tackle search problems on graphs. The most simple continuous time quantum walk was the quantum walk introduced by Childs and Goldstone, but it does not provide quadratic speedup with respect to the classical heating time for all graphs. But in this work, using a more general continuous time quantum walk, so in particular, an important difference is that we're not working on the vertices, but we're working on the edges. We can get a full quadratic speedup for any possible graph, and therefore get the same properties as for discrete time quantum walks. Okay, so I will stop here. Thanks a lot for your attention, and I'm of course open for questions.
Are there any questions for Jérémie?
I have one. Yeah, thanks very much. So my understanding is that the non-unitary operator is a linear combination of unitaries requires some stringent bounds on the operator norm. And I was wondering if that's the case, and if you had to rescale, by an overall factor to make sure your operator norm was bounded by, say, 1, whether that affects the time for the walk.
Okay, so essentially, this is where this success probability comes from, because you do not get indeed. I know I was very fast. I'm sorry, but essentially, since this, of course, each element in the sum here is a unitary, but the convex combination is not a unitary, which means that to make it unitary, actually, you just enlarge the Hilbert space, and you only get the state that you want in some part of the Hilbert space, but then you also get some amplitudes on another orthogonal state. Okay, and this means that actually here it's the actual success probability here is given by the norm of this part of the state, and the norm is indeed less than 1, and this is related indeed to the L1 norm of this coefficients, and this is where this non-unit success probability comes from. Okay, but hopefully actually, and this is why we need to pick the right S here, because if S is too large, then this becomes too small. And if S is too low, then we do not have enough overlap over the Mach state. So there's some kind of compromise over S in order to get this high enough success probability. If you want.
Other questions?
I have a question.
Yes.
So your Hamiltonian is composed of the Mark vertex plus an interaction factor of the Laplacian, right? You were mentioning a while ago.
Okay, so
that was way before, I think, at the middle.
I think what you mentioned is Childs and Goldstone Hamiltonian.
Yes,
right?
Correct.
Yeah, so this is not what we're using. So for Childs and Goldstone, it's the Hilbert space is just given by the positions over the graph. So you're really working on the vertices of the graph. Here, just as for the right slide where I can explain this. Yes, here we're working on pairs of vertices, so on edges, if you want. So the Hilbert space now has 2 copies of the vertices. Okay, and so here this slide is for the discrete time quantum walk, but we have the same interaction for the continuous time quantum walk. You get a coupling between 2 edges if they have a common vertex between them, and this coupling is essentially proportional, if you want, to the weight of the edge, to make things simpler.
I see, but my question, Jérémie, though, is that for the Childs-Goldstone approach, I was wondering, because you have the gamma, right, factor of the Laplacian. I was just wondering if you can change that as a sort of instead of gamma L, you have a linear combination of the degree matrix and the adjacency matrix, because the Laplacian is just D minus A. So instead of gamma D
Okay,
minus
you would
gamma
like to replace the Laplacian by, so you would like to put different weights on the diagonal, right?
Yeah, that's right.
Yeah, I think it's kind of related to the question that Tom had for his talk. I don't think it will make a difference because essentially you will just, so I mean, there are two options. Either if the graph is regular, all the degrees are the same.
Mhm.
And therefore, in that case, just changing this will change the diagonal of your matrix. So essentially, it will add a multiple of the identity to your Hamiltonian. And so this will just change the phase of your dynamics. So it will not change the dynamics.
For the regular ones.
A multiple of the identity to Hamiltonian. Physically, it does just a shift of energies. Okay. Now, the other case is when the graph is not regular. In that case, all the degrees on the diagonal can be different. And in that case, it means in a sense that you would have the same effect as marking. So the vertices with higher degrees, it means that you put a higher energy penalty on them. So it's as if you were partially marking them. So I think it might mess up the work. I'm not sure what would happen in that case. Okay, because you see here what you do is you add an energy penalty on the diagonal corresponding to the marked vertex. If you increase the coupling with the degree, this diagonal degree matrix, you will just add such an element for all vertices. So it's as if you were partially marking all the elements. So I think it will mess up the search, but I'm not sure. It could
have an idea of what happens or regular.
If it's not regular, so I don't know. I don't know. Maybe Tom knows actually, because he has also studied this kind of things. Well, he left, I think. He left.
He left, yeah.
Yeah, but I don't know.
Thank you.
Further questions? If not, let's thank speaker again.